get started. Hello, everybody, and thank you for joining us today for IEEE Young Professionals webinar. Our speaker today is Joanna Hill, who will be presenting the webinar entitled, Dorothy, we're not in Kansas anymore. We are in Impedance Land. Oh my. Next.
Okay, there we go.
So, again, welcome to the third Young Professionals webinar of 2014. My name is Mario Milicevic, and I'll be your host for today. I'm Vice Chair of Products and Services on the Young Professionals Committee, and I also serve as the Chair of the Toronto Young Professionals Affinity Group. Now, the Young Professionals will be hosting several webinars in 2014 on the topics such as effective communication, leadership, humanitarian outreach, and many more. And just here, our humanitarian outreach webinar is next week on April 10th. Next. Here on the etiquette for this webinar, we kindly ask that you please mute your microphone. You can do this by pressing *6 on your phone or muting the WebEx. And so, during the webinar, Joanna will be very happy to answer any questions that you have related to her talk following every slide. So please do type the questions that you have into the chat box, and Joanna will answer them at on. There will also be a 5 to 10 question and answer session at the very end of the webinar. So if you have any further questions, you'll get a chance to ask them then. More, you can email Joanna at the email that's included right on the screen if you have any further questions after the webinar. Next, I want to say is that the IEEE Young Professionals is a brand new name within IEEE. We were formerly known as the graduates of the last decade, and as of this year have rebranded to be more globally recognizable as IEEE Young Professionals. And this new name really makes it easier for members and prospective members to find information relevant to their early career interests. Successes globally related to the name and the rebranding. Toronto, for example, just last week we had a very successful networking mixer that was attended by over 250 people from the engineering, sciences, business, law, and arts and media industries. There was a networking mixer held at the South by Southwest Festival in Austin, Texas earlier in March. And there was also a networking event launched at GHTC at Santa Clara back in October. If you do want to follow all the updates on Young Professionals, please do note the Gold Rush blog at IEEE.org/YP. Now, it over to Joanna to conduct the webinar. Thank you.
Well, I'd like to welcome you to Impedance Land. As you know that you don't have to be crazy to get into EMC. We will train you. What we are the 10 rules of Impedance Land. They are the Golden Rules of EMC. The first is about wavelength and not frequency. Wavelength is something that you can hold in your hand because you can measure the length of things. Frequency is a bit nebulous. Second, and the thing that your boss is going to be most interested in is that the longer you wait to fix EMC issues, the more you're going to pay to fix them. Third, and something that a lot of people have trouble with, there's no such thing as ground above 100 kilohertz. It exists. 4, the conductors that you know and love, the wires and the various conductors, all have length. They have phase change across their length, and they have inductance. And they have 2 conductors that are separated by a dielectric capacitor. Quite important, and quite often we feel EMC because of it. That is, never use any more bandwidth than you need. So we want resistors rather than capacitors because we don't want to play whack-a-mole capacitor, and we'll get to that in a moment. We keep our node impedances below 10K, and when we can't keep a node impedance below 10K, we need to look at it very carefully to make sure that it will work correctly. Is that fractional wavelength is one thing, and dimensions near a wavelength is another. It's two completely different worlds that you look at the EMC issues in different ways. But welcome to the brave new world above a kilohertz. We're talking about a tank circuit. You have resistors and capacitors, and it's the interactions between these two components that will determine if you pass or fail EMC. And there is a wire. It's anything that's conductive. That is anything that is conductive. And a capacitor is simply two conductors separated by dielectric. Conductors is the steel structure within the building that you're more than likely sitting in at the moment. The wall steel in it, they have conductors. The ceiling tiles are in place by a grid of conductors. These are all conductors. They all have inductance. On the bottom left, you see a picture of a BMW where is capacitance between the conductive floor of the screen room and the metal of the vehicle. You calculate what that capacitance is, and you can know what that tank circuit is going to do when you connect the wire to the vehicle. The tank circuit that I know of is a thunderstorm, which is conductive because of the ions in it, and you have the ground, which of course is conductive. It's separated by a dielectric, which is the air, and so you have a capacitor. The capacitor can store charge, and when you have a conductive path formed by the lightning, there is inductance in that lightning path. And so if you have a tank circuit, and you look at that current flow, you will actually see the ringing of that current flow. It's a circuit. Or to get your products to pass EMC, this is probably the most important slide in the presentation. It's surprisingly simple, and that is you have a tank circuit, you have an inductor and a capacitor, and you have a third component, the resistor. The resistor is going to determine what the current is going to be at the self-resonant frequency of this tank circuit. When you have a tuned tank, if you raise the value of that resistance, the current goes up. But in a tank circuit, if you raise the value of resistance, the current goes down. That fundamentally will give you a clue as to how to solve the EMC problems. Instead of resistors, the value that you need will fit EMC issues. Energy going between that inductor and that capacitor. You're storing on the capacitor and you're storing energy in the magnetic field of the inductor. Going back and forth. And when back and forth, we can set the period of cycling of energy. And of course, the frequency 1 over the period, and that's all review. But it is going back, causing a current that is actually causing the harmful interference. That creates an E field, radiates into free space, and other products can be detected and have caused harmful interference. If it happens to be a big motor that's interfering with land mobile communications because the receiver hears that field, that's CC. Couple energy into a tank. If you think about it, at the self-resonant frequency of that tank, it depends upon the resistance in the tank. Is the resistor in series or is there parallel? So the electromagnetic compatibility is the current is in these tank circuits. Tank circuits are everywhere. How do we fix an EMC problem? Only three things that we can do. The first is shut down the source of the energy. The source is noisy brushes in a motor or a frequency clock in a computer. That source of energy, if we shut down the source, we fix the EMC issue. But obviously we can't shut down the source of a clock inside a computer. You have to have a clock. Oh, that means something else. What we can do is we can interrupt the coupling between the source and the antenna. And it's an antenna. And the trick and the EMC issues is locating the antennas and breaking them. So you need to understand that. I heard that question. If you could send it in writing, I'll be able to read it. Again? To continue here. All right. So the concept here about stuff, and that is distance, phase, and inductance. It's all the same stuff, the EMC. And then you have a conductor, and the conductor has a lane. The distance that you travel as you travel across that lane. Travel across the length of a conductor, the phase of the signal inside a conductor rotates. It changes. And we model that as inductance. So you have an inductor sometimes as a component that you buy from DigiKey. But to me, an inductor is any conductor that has length. The EMC is understanding how these three things relate to the wavelength. You have an EMC issue, it's at a specific frequency. You calculate the wavelength, and you look at how that relates to distances, the physical distances, the physical phase changes, and the way is inductance within our circuits. So wavelength. Wavelength is equal to c, the speed of light, divided by the frequency. We could have kind of an okay definition, but an EMC engineer and an RF engineer, we need one that's a little bit better. That definition is that the wavelength is the distance traveled by a propagating wave in one cycle. EMC and you're working with RF, you always have to maintain the idea that these fields are moving through free space. And they relate the distance being moved to the frequency of the signal. So a really simple equation that you can use that you're working EMC issues in order to understand what the wavelength is. So this is equal to 0.3 meters divided by the frequency in gigahertz. Okay? If you use that in English terms, it's 11.8 inches divided by the frequency in gigahertz. That's a way of saying that within free space, this will travel 11.8 inches in 1 nanosecond. Okay, messy, and there's a lot of information here which is probably review for all of you. Requesting remote control. Is everyone there?
Okay, I think you can continue.
Okay. So this slide is a little messy, but there's two things you need to remember on this slide. First one, over there, the permeability of free space, and that is 8.854 times 10 to the minus 12 farads per meter. The magic number that you need in order to calculate the capacitance of a computer, and that is you run a circuit board. It's above a ground plane in an automobile. What is the capacitance between the ground of the circuit board and the automobile. Well, calculated using this number. Remember that the velocity within free space is c, the speed, but the velocity when you're not in free space is equal to c divided by the square root of relative permeability and the relative permittivity. Important one, you need to remember it. Okay? Many design products that use FR4 printed circuit boards. The speed within an FR4 board is equal to 0.48 times the speed of light. Is there a question? Continue. See a question pop up in the chat box. So the wavelength within a printed circuit board is not 11 inches as it is in free space. It's 5.9 inches. Because I see gigahertz. That are for materials, the speed of the propagation is 5.9 inches in 1 nanosecond. Page of an antenna book. If you remember, I mentioned that antennas in them is the key to understanding how to fix EMC issues. Okay. When you need to be able to know what makes a good antenna in order to be able to know how to break it. So a little bit into what makes a good antenna. First off, you have a wavelength dipole. We were told that dipoles are half wavelength. In fact, if you make a truly half wavelength dipole, you can find out that it's not truly resonated. It's an impedance of 73 ohms plus J 42.5. In order to make that dipole a truly with dipole, well, what we'll do is make the length equal to 0.475 times lambda. Dipole that acts as the correct frequency, which is 67 plus 0. We want it to be completely real in order to be a good antenna. We've been as wires, and the antennas in a variety of locations are wires somewhere. But the most important antenna that you're going to find within your products is not a wire, but it's the absence of a wire. In a ground plane is an antenna. And if we did specific antenna in a little bit more detail, we got that the length of 0.925 wavelength times the wavelength, and then of 0.066 times the wavelength provides us a perfectly 50 ohms J0 antenna. Think about that. It means that we have a 555 millimeter long slot and millimeters wide. You have a wonderful 500 megahertz antenna, more than a hole in a ground plane. This is key to understanding how to solve EMC issues. And this is why. The good, the bad, and the ugly. That on the right, it's EMC miserably. 23 dB over the limit. It's very badly. And so they fixed the ground plane, and that's the bedboard in the center, and improved it quite a bit, but it was the limit by a few dB. And then the left is DMC. What's these two boards? Well, the magnetics are completely identical. Only difference in these three boards is the ground plane and how it's routed within this two-layer FR4 printed circuit board. Here is the far right. The far right ground is a daisy chain. and hence makes a wonderful dipole antenna. In this, if you this ground plane on the little bit there, right there, a big slot in the ground plane. This is a dipole antenna set at this point right here at the top of the dipole. And that is why it failed. So in order to ask the EMC, this is the ground plane that you need. Notice that the slots have been turned into small openings in the ground plane. All right, what we're going to do is convince that you do not want to play whack-a-mole capacitor. And whack-a-mole capacitor. Well, let's talk about capacitor. And they're connected with two wires. So you have a tank circuit here. You can calculate the fringe tank circuit and estimate the inductance of the circuit board at 15 nanohenries per inch. Now, some people will be talking about that value as being 10 nanohenries per inch, and I'm not going to argue the tiny little details here. E is a science of order of magnitude. You get the right order of magnitude and you pass. When we add a third capacitor, well, it's a little bit more complicated because in this system, you have one tank circuit, you have a tank circuit, and you have a third tank circuit. Each of the tank circuits can resonate and have high currents cause emission that makes you fail the EMC. What happens? We have 4 capacitors. Okay, 4 capacitors gets really ugly, and you have 10 different resonant frequencies. You have 12 different current mode paths between these tank circuits. So if one tank circuit is resonating, it causes current in another tank circuit. So we don't play whack-a-mole capacitor because you look at a board and you have an emission at a specific frequency. You grab a capacitor and you it. You put that on the printed circuit board and you solve that frequency's problem. But suddenly, other frequencies popped up along the side, and you whack at that with another capacitor, and then another capacitor, and another capacitor, until finally your boss is asking you, is it that your board is full of capacitors, and you're still failing EMC? Well, what you got to do is find those loops and example of a product that we had an EMC issue on, and we're going to play pin the tail on the tank circuit. This had a failure at 220 megahertz, and we'll find out where the failure is and how to fix it. Tank circuit, and I'd like you to take a look at it. It's embedded in this schematic, and I want to know, can you find the tank circuit? I'm going to take a look at this circuit. You tell me, where is the tank circuit? It's there. Can you see it? You have some there. There's if you value of resistance, the performance got worse. Okay? Where's the can you see it? It's their circuit. It's got tail pins on the donkey. Okay. Those pictures have a capacitance. It's a small capacitor, but it's capacitance, and it's approximately half a picofarad. They have inductance. And important here, The input to the microprocessor on pin 50 over there on the far right is a capacitor. It's a transistor, and gates have capacitance. In numbers, to estimate the capacitance of an input on a microprocessor, it's somewhere between 5 and 10 picofarads. I picked 7 just because you got to pick a number somewhere along the way. And again, remember that EMC is a game of orders of magnitude. And pin 34, that is a driven output that's being driven to a 1 or a 0. In either state, you have an RF ground at that point. So you have to calculate where this loop is going to resonate. In order to do that, we need to know what the capacitance of that non-conducting diode is. In this failure, it was a susceptibility failure where when you light RF to this circuit, it did switch depression all by itself. All the RF that made this circuit think that someone had depressed the switch. So that it was off, and what the capacitance of an off diode is. Sheet shows that this roam diode has a capacitance of 3.5 picofarads. It's a piece of data. So let's calculate the resonant frequency of this tank circuit. You have a picofarad capacitor, you have 7 picofarads of the input to the processor, and you have 3.5 picofarads of the diode. Hence, 15 nanohenries per inch times approximately 20 inches of conductor. So that's approximately 300 nanohenries of inductance, and the self-resonant frequency calculated here is at 188 megahertz. Well, 188 megahertz is close enough, 220 megahertz, to say our estimates of these parasitic values is proving that this tank circuit is the tank circuit that's causing the EMC failure. So how do we fix it? Well, how to fix it is to be a good witch, and that is to, rather than this situation as black magic, we look at the situation as a wood and use our basic skills in electrical engineering to know that we need to put a series resistor in this tank circuit. But we know exactly what the value of that resistor needs to be. We could set the value and try, 10 ohms, 100 ohms, 50 ohms. Okay? Guess at what that value needs to be in order to solve the problem that we have in EMC. Others are going to expect us to know what value that resistor needs to be in order to solve the problem. To do that. We can, as a mathematician, do some work solving Maxwell's equations and make some assumptions. The that he made was that the loop of is small as compared to a wavelength. Remember the rules is we have a fractional wavelength antenna. So when current is significantly smaller than a wavelength, it is a fractional wavelength loop antenna. A conductor that is a monopole or a dipole antenna that is much, much shorter than a wavelength, a fractional wavelength higher. So closed form expressions for the field maximum that's going to be made by a small loop short wire. These are fundamentally important to your ability to calculate what resistance that you need to add into a circuit in order to pass EMC. This equation that comes out of from the most important EMC book that has ever been written by Henry Ott, that I recommend. And this equation, it is a form of the equations that I just presented. So from these equations, with it right there, where 20 times the log of emission 1 divided by emission 2 is equal to 20 times the log of the resistor 2 divided by the resistor 1. An emissions problem or a susceptibility problem, and we need to improve it by 10 dB or 20 dB or whatever the value is. What value of resistance change you need to make in a circuit in order to solve the problem. And then equations for a small loop. Again, the division resistance needs to be 20 times the log of R2 over R1. So the problem, we found our tank circuit and identified that it is the one causing the emission at 20 megahertz. What resistance do we need to put in that circuit in order to make it work correctly? Well, take a guess. We look at this equation and we say, okay, we put in a 100 ohm resistor. And the resistance of copper and the various inputs of the Q of the input to the microprocessor, we take all of that into account. If the series resistance before adding the resistor was 100 milliohms, and we add in a 100 ohm resistor to the input to the microprocessor, the digital guys are going to tell you that resistor isn't going to do any good because there's no current in it. But that's not the point. We're using the resistor here to DQ the tank and it'll pass the EMC. So with a new resistance of 100 ohms and an old resistance of 100 milliohms, we would expect an improvement of 60 dB. That's it dead, as Henry talks about. We want EMC issues dead, not fixable. We want them to totally go away, and this is how you do it. Now, the resistor is going to have a parallel capacitance to it. So you're not going to see 60 dB of improvement. You're going to see something less because of that parallel capacitance between the two terminals of the resistor. Now, extra credit, I'd like to look at this circuit because there is a second tank circuit. And look at this circuit and tell me where the second tank is. Option here. What is different as small loop and a wavelength? Yes. Absolutely correct. A small loop that is 1/10 a wavelength, that's the dividing line that many people use in order to determine a small loop versus a larger loop. It's not a hard and fast. Okay, I'm audio from the audience, which is John. It's not intelligible. Could you please? I'm not hearing anything, so if you would please into the chat box and I'll answer the questions. So, what small fractional wavelength versus large? There is a definitive point there. I'm not talking about something that has a cliff that we fall over. It's a continuous thing. And a wavelength is a good point, but it's hard and fast. Come back to this tank in this tank circuit. by that wire right there. There is a capacitor C67 in this particular schematic. It's on the far side of the diode. So the tank circuit formed from pin 34 of the microprocessor for the C67 and that microprocessor's output through the ground structure. Now we have a common mode impedance between two tanks. It means that if that second tank resonates, it will insert energy and it's going to be a wonderful antenna because so a signal can go off to a very long antenna. Okay, come back to the 10 rules, the Golden Rules of EMC Land. And what do you mean? What are the takeaways from this presentation? The first thing to do is think in terms of wavelength, don't think in terms of frequency because frequency is nebulous. Cycles per second. How do you hold a cycle per second? You can't do that. But you hold 6 inches of wire, you can hold a meter of conductor. The second is the longer you wait to EMC issues, the more it's going to cost you in your development cycle. You wait to the very end, the weeks before you're going to go into production, and you are going to pay lots of money for laboratory times. Your boss is going to be all upset with you. The schedule is going to be trashed. The budget is going to be trashed. And in general, your boss is not going to be a happy camper. So see issues or you will pay. There's no such thing as ground above 100 kilohertz. What that means is that 100 kilohertz, and again, this is not a hard and fast, over the cliff kind of thing, but in around 100 kilohertz, circuit as a DC circuit to fail, and we need to think about it in terms of an AC circuit. Doing audio, you think about that kind of like the way you do a DC circuit. But if you have 150 kilohertz because you have a near-field communication channel, like one between your credit card and the reader that reads your credit card, that's something. The ground plane just is not a single point. That ground plane has length and wavelength, and so there's no such thing as ground above 100 kilohertz. Number 4, all colors have length. They have phase change along their length, and hence model that as an inductance. Think about that. That's really very powerful. And the length of the wire is what's important here. Ceiling tiles that may be above your head right now, there is a grid of antennas above you. Each that holds up that tile is a conductor. There's a them, and hence that's a loop antenna. Although the length of each one of those conductors is phase change, and total distance around that loop is equal to wavelength, you have a full loop antenna. Conductors have length, phase change, and their inductances. Number 4, anytime you have two conductors that are separated by a dielectric, you have a capacitor. Be out in the ground in a lightning storm, or if a vehicle on top of a ground plane inside a semi-anechoic chamber. Never, ever use more bandwidth than you need. When you go and you put down on a board a transistor has 500 megahertz worth of SFT, which is a measure of the transition frequency of a transistor. It's the gain, the AC gain of a transistor goes to zero. Goes to zero or unity. At a 500 megahertz, and a circuit trying to pass a pulse width modulation that is at 200 hertz. If you 100 megahertz transistor, in order to do it, it can fail EMC unless you mitigate, you throw away that extra gain that you don't want and simply gets in the way of passing EMC. And you don't want to play whack-a-mole capacitor and one capacitor after another, and have your sorry. And you're all upset with you because you're playing whack-a-mole capacitor with you're doing a whole lot of changes, you're adding a whole lot of cost to your product, and you're not fixing the problem because every time you add another capacitor, you add the possibility of numerous to be formed, and each of those tank circuits can cause emission or be a cause of a susceptibility. So whack-a-mole capacitor. 8, keep your impedances below 10K, and you can't keep your node impedance below 10K. Look at that circuit very, very carefully before you put a product in the test. And make it from an engineering point of view, understanding the antenna structures that are being formed. Is antenna going to be a good antenna, or are you going to break it and make it a bad antenna so it doesn't cause you EMC issues? The fractional wavelength. That was part of the question from before. 1 wavelength or is fractional wavelength. Here, a wavelength, you have to think of that in terms of a fully functional, full antenna, or a loop antenna, or a pole. So we're looking at an EMC issue in terms of, okay, what is the frequency, calculate your wavelength, and know what physical lengths. You know there is going to be this dividing between the way you look at things as a fractional wavelength situation versus a full wavelength situation. Importantly, and I hope that through the presentation you feel a little bit more about solving the problems of EMC and not having them be witchcraft. The brave new world above 100 kilohertz. End of the presentation. I thank you very much for listening to it and giving us to introduce you to Impedance Land. So if please ask your questions at this time, unmute your mics, and go ahead and let me know what kind of things you'd like to know about.
We'd like to invite some questions for our speaker, Joanna. So if you have any questions, please go ahead.
We want to put caps, put it very close physically. Yes. Put a capacitor close physically. It depends a little bit upon the product. The die constant of FR4, which actually is a complex number. So it's real and imaginary part. Constant loss tangent, which is part of that dielectric constant. Measuring loss C, the dielectric is, falls pretty quickly up gigahertz. So what we do is by putting the capacitor so physically close to where it needs to be, we make that loop very small, and we make the self-resonant frequency of that loop high. We want to get that loop above gigahertz. Most products that are used today, if you're dealing with a very fast microprocessor, you need a capacitor that has more than 2 leads. There are capacitors out there with 8 leads to a single capacitor in order to make that inductance between the capacitor and where it needs to go significantly smaller. So yes, we want to put the capacitors physically close to where they need to be. And how do you troubleshoot? The package is already sealed. I can go to the board. Okay. Pull the trick. You go to a fabric store near you that sells sewing supplies. They sew pins. They have a little head on them that you can grab onto. And often when you have a product that is packaged in a conformal coating, you can use straight pins to poke through the conformal coating and actually make electrical contact. You can't get through that because you have, say, hard plastic that you're encapsulating with. You near field probes in order to get an idea of where the emission is coming from. There are very sophisticated near field probing systems which can provide X, Y, and Z mapping of the emissions from a product without ever touching the product itself. So that answers your question. Other questions? Wow. You're welcome. I very much enjoyed providing this presentation today. It has given you some insight in the EMC and to understand that the witchcraft of EMC doesn't need to exist. Use the skills that you have gained in your electrical engineering programs, your degree programs planet-wide. Use those skills and think of terms of the capacitance that are formed, the inductances that are there. Calculate the inductances, calculate the capacitances, know your tank circuits are, and all the problems of EMC before you ever go to the test. And if you have a problem that shows up in a test, calculate the wavelength of that problem and what physically the distances are that would make a quarter wavelength and a half wavelength and a wavelength. If you have a fractional wavelength situation, you know what to do. And if you have a full wavelength situation, you also know what to do. Look at the antenna structures. So thank you very much. I appreciate that you've been able to see the presentation, and let me know if you have any further questions by email. Okay? Thank you for listening.
Thank you very much. Fantastic webinar. I have one more slide to conclude this webinar. So thank you for listening. We hope you learned something new. I definitely did. And we kindly ask that you complete the feedback survey, which will be emailed to you shortly after this webinar. I will mention that our upcoming webinar is next week on Thursday, April the 10th at 12 p.m. Eastern Time on the topic of technology-enabled humanitarian frameworks. We have 2 brand new career-based services available for young professionals. These are the IEEE Mentor Center and the IEEE Resume Lab. And you can check this out by checking out the web links provided. Any further suggestions on other young professional products and services that you'd like to see, please drop us a line at youngprofessionals@IEEE.org or visit at IEEE.org/YP. We thank you for listening and hope you have a great day.